Hi, welcome to Chapter 3 Notes on the Structure of the Atom. In this section, we're going to be talking about the general structure of the atom and how we use the protons, neutrons, and electrons to identify different types of isotopes. So it's basically using our periodic table, so you do want to make sure you have that available so that you can use it. So the first thing we want to talk about is what is an atom? Typically in class, I like to describe the atom like a Lego. It's like a single Lego that you're using as a building block to make other things. So an atom is really just the smallest unit of matter that we have. So there are things smaller than the atom, which we've learned about in our atomic theory section, but it's basically your smallest complete unit of matter that you can use as a building block is a singular atom. Atoms can combine together to make larger samples that we can see. So if they're all the same kind of atom, that's a pure substance, like an element. But we also can combine atoms chemically to make larger things like molecules. All right, so all atoms, individual atoms, are going to have three main subatomic particles: protons, neutrons, and electrons. So you can see from the picture over here of kind of where they're at and what they're located. The little green negative sign is the electron, the positive blue is the proton, and then the neutral red one is the neutron. So for protons, typically what we would write for our symbol is I would write a P with a positive charge. What that tells me, that lowercase p, that's usually a lowercase p, that lowercase p tells me that it's a proton, and we can see that protons are found inside the nucleus. And they have a charge of +1. And actually, their relative mass, we'll talk about in just a moment. Neutrons are going to be an N with a 0. The 0 means there's zero charge. A neutron is chargeless or has no charge, but it is also found in the nucleus with the protons, as you can see in the atom example. And the electrical charge of it of course, is 0. Electrons are going to be an E, a lowercase e with a minus sign. The E with a minus sign is telling me that the electrical charge is a -1. Notice protons are found circling the atom. They're not technically circling, but surrounding the atom in the empty space outside of the nucleus. And we'll talk about electrons a lot this year. All right, and each of these have their own relative mass. A relative mass is not their true mass. Protons and neutrons and electrons are so small that we can't actually, we can calculate what they should be in terms of mass, but we can't put them on a balance. So a relative mass is what we use when we talk about them in relation to each other. So the relative mass of protons and neutrons are both 1 AMU. AMU is the unit for a relative mass because it's not a true gram mass unit. And electrons are going to be considered, or actually the relative mass is 1 out of 1,840, which that's super small. That's like a tiny, tiny fraction. So that's basically 0 AMUs. We pretty much ignore the mass of the electron, even though we know it does have mass because all matter has to have mass and take up space. But we pretend it doesn't because it's so small that when we're looking at the mass of the atom as a whole, it doesn't really contribute enough for us to notice. As you can see where each of these are, this is a nuclear model of the atom. There's a quick showing the nucleus. There's a quick early atomic review here. I just want you to take a few moments and I want you to try those on your own. So I want you to take a few minutes and see if you can remember from the previous unit who discovered what, and how they discovered them. These are some of the important things that you need to make sure you know. So take a moment, pause me, and then come back and check your answers to see if you got them correct. Okay, so check your answers, see how you did. You can see Rutherford discovered the nucleus, and he used the gold foil experiment to do so. Now, Democritus was the first person to propose the idea of the atom, and he also believed that atoms were the smallest unit or building block of matter, and so I put B for him, even though I also put it for Dalton, because Dalton did believe that the atoms were indivisible and that there was nothing smaller than the atom, and he also believed that you can rearrange atoms in a chemical reaction, but the atoms remained the same. They just changed how they were arranged. Then Chadwick didn't do a whole lot. Chadwick, there was no real experiment for him. He just made the observation of the discovery of the neutron. And then Thomson used cathode ray tubes to discover the electron, and then he proposed the plum pudding model of the element, or the atom, which looks like the chocolate chip cookie model. All right, so let's talk about what we can use this information that these men discovered for us, and how we can use this information to help us look at atoms individually as elements. The mass of an atom is going to be confined to where? So based on the picture I showed you, where was all the mass? The mass was all with the protons and the neutrons, which means it's in the nucleus. And the electrons have negligible contribution, which we talked about. They're so small that we just ignore them in terms of mass. But we can see that the nucleus is really, really small and dense. And from Rutherford's gold foil experiment, we did see that the beams of alpha particles were traveling towards the nucleus, but most of the time they passed straight through the atom because a large portion of the atom is empty space. There's only a small dense portion, that's the nucleus, that the alpha particles were bouncing off of or basically hitting. So the electron fills most of the empty space. Remember that your atom is mostly empty space. You can definitely see in these different examples that are down here, the electrons take up a lot of space, whereas the nucleus is very small and dense. And this doesn't even give it a good representation of how small it is. There's actually a TED Talks that discusses how small the atom is that is great.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? Well, it's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class, where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
So as you can see that is a great representation of how small the atom really is. So as we were discussing, the mass of an atom is confined to the nucleus, which is what you saw in that video, and you can also see the electron has negligible contribution overall to the mass because the electron is really super, super small, but it's filling all of that empty space that he was talking about of the atom. So when we look at individual atoms, every atom has a unique way to identify it. And that is based on the atomic number. The atomic number is actually the number of protons that are found inside the nucleus. Every element has a set number of protons that we use to identify it. So the atomic number can be used to identify which element it is. So if you look at the examples over here to the right, you can see that hydrogens have 1 proton, oxygens always have 8 protons, and sodiums always have 11 protons. So we can use protons, which is the same thing as the atomic number, to identify it. And on a periodic table, that's going to be the number that you're going to see written at the top of the periodic table itself. So for each individual element, it'll be written at the top of that element. If an atom is electrically neutral, we also know that protons must equal the electrons. Now, the reason we know this is because to be neutral means we balance out, or there's no overall charge. So if I have positives, then I also have to have negatives to balance them. So for every proton, there also must be an electron in that empty space to balance it out. So the why here is because atoms are neutral. We will talk later in the year about when atoms are not neutral, but for right now, we're only going to be discussing the neutral atoms. So if we know our number of protons because we know what the element is, or the atomic number is, then we can also know the number of electrons. The other thing we know is the mass number. So we know that the mass of the atom is confined inside the nucleus. The mass of the atom comes from the protons and the neutrons that are found inside that nucleus. Remember that we said that the electrons have negligible contribution to the mass. So a mass number is always written as part of my element name and symbol. One thing to be really careful about is this statement right here. Mass number is not indicated on my periodic table. Students tend to get confused on this. There is a mass on the periodic table, but that is called atomic mass. So you need to make sure you make it clear to yourself that atomic mass does not equal, mass number. Mass number is important for us because it tells us which specific type of each element we're talking about. So, for example, when I see the symbols written below, the names and symbols, whenever I write a name, the name will always have the mass number coming after it. So for potassium 40, it would be the name, and then the 40 tells me the mass number, or the number of protons and neutrons that would be found in the nucleus of that potassium atom. It's important to know that neutrons can change. Protons cannot, but if you notice, neutrons can change. So some oxygen atoms have 8 neutrons. Some oxygen atoms have 9 neutrons. So the number of neutrons can change because those are a neutral particle, which we're going to talk about in just a moment. So when we know that the number of neutrons can change, so that means the mass number can change. So we must always write our names with the mass number following it to indicate what it is. It is not the number on the periodic table. The other thing is when you write your symbols. When you write your symbol, whatever it is, I'm just going to make believe X. We will always write the mass number on top of the symbol because that's specific to whatever of the elements that we're talking about right here, whichever atom we're specifically talking about, and then the atomic number on bottom. Sometimes books will leave that atomic number off because you can look that up on a periodic table, but the mass number should never be left off because we can't look that up. It has to be given to us in some way. So in this example, it wants you to write the element. It's giving me the element name for potassium 40, and it wants me to write the symbol. So if you're going to write the symbol, you would look on your periodic table, and the symbol for potassium is a K. So we write our K, and then we have to make sure when we write the symbol itself, we have to put the mass and the atomic number on the left. Mass number will always go on top. Atomic number will always go on bottom. So we're going to look up the atomic number for potassium, and I looked that up, and it's 19. So, oops, I wrote that in the wrong spot, so make sure you don't do the same. All right, so we look up the atomic number, and it's 19, so it goes on bottom, and then the 40 for the mass number is going to go on top. So I will be able to look at this and be able to see the larger number, which is the mass, should go on top because mass should be larger. Mass is protons and neutrons, whereas the atomic number on bottom is just protons. So mass number should always be larger than your atomic number. Then if you look at nickel, on nickel we're trying to write the name here. So Ni, of course I just told you, is nickel. You should know this or be learning these because we're going to be quizzing over it. The nickel, we can't just write nickel because there is an important part of nickel that we have to make sure we include, and that is the mass number of nickel. So it'll be -58. Whenever you write a name, you must write the mass number following it. So nickel -58 becomes important because this is a certain kind of nickel, and there are other kinds of nickel that have different mass numbers. So in this case, it's really important for you to practice and make sure that you are making your symbols and your names exactly like mine, especially on practice problems and quizzes and tests for this chapter. Because in this chapter, we're going to be talking about these kinds, the different kinds of nickel or potassium or atoms that we have called isotopes. So isotopes is on, we're going to continue on the next part of the notes. So if you flip over to your next page, we'll talk about them. So the name and the symbols are really important because the name and symbols allow us to identify different kinds of isotopes. So if you look at the lithium example here, and I've also got, this is an example of carbons. I gave you 2 different pictures just so you can kind of see it. But the lithium example, do you see that there's 1, 2, 3 kinds of lithium? Each of lithium's atomic numbers are the same. But we can see that the mass numbers on top are different. These are called isotopes. They're all lithium. And typically, like, our body wouldn't know the difference between the different kinds of lithium. So they all act exactly the same. But the mass numbers of these different isotopes tell us that there's a variation in them. It just means that they have a different number of neutrons. That's important to realize because the proton number has to stay the same because atomic number is staying the same. That means protons must be the same. The only thing that can vary here with the mass number must be the neutrons causing that change. So the neutrons are neutral, so they don't really affect the overall isotope very much. So an isotope is an atom of the same element, which means it has same atomic number and same number of protons that have different mass numbers. That's because their neutron numbers are different. The carbon also has 3 isotopes. Some elements have more than 3 isotopes, and some elements don't have any isotopes. It just depends. So here's one example, and then I'll have you do one. It says, write the name and symbol for an isotope of silver with a mass number of 107. So first thing we need to consider is how many protons, how many electrons, and how many neutrons are in this atom. So if it's silver, my silver element is Ag. The 107 is its mass number. So when I write that symbol, I write 107 on top. And then I look on my periodic table for Ag, and so that is 47 for its atomic number. So that would be the correct symbol. If I have the symbol, I can figure out the protons because the atomic number is equal to the protons. So we have 47 protons. What do we know about electrons? Protons, if the atom is neutral, which we're assuming it is, if protons are 47, my negative electrons have to balance them, so they're also 47. Now, the only one that's really tricky to find is the neutrons, and it's really not too bad. The neutrons, you have to take the mass number, which is on top, and you subtract your number of protons, which is your atomic number, and when you subtract those, 60. When you subtract, that's terrible. When you subtract your your protons from your atomic number, you get your number of neutrons. So all you're doing is mass number minus protons will give you the neutrons that it took to make that mass. You also could plug into the equation just mass number equals protons and neutrons and just solve for neutron, whatever you prefer to do. This is not something that you would have to show me curse on. I just expect you to be able to do it. All right, so take a moment and try B. I'm going to be checking to see. So pause me. I want you to try it yourself. I'm going to check to see if you did it right. All right, so what do you see? It says, why are the isotopes? So how many protons are in the atom? 47 protons and 47 electrons because it's still silver. Silver is going to have the same number of protons and the same number of electrons. Now the neutrons are going to vary because it has a different mass number. So when you take 109 minus 47, you get a mass number of 62. So why are the isotopes the same? Take a few minutes. I talked about this a minute ago and answer those questions. So go ahead and pause me and answer the questions on your own. All right, so check your answers. Isotopes are the same because they have the same atomic number, which means they have the same number of protons. And why do the isotopes have a different number of mass? The different mass numbers are because there's different numbers of neutrons inside that nucleus. So in summary, take a moment and I want you to summarize these. I want you to tell me what this info is. So for the atomic number, you're going to tell me atomic number equals, mass number equals, which I actually wrote already for you, and then in a neutral atom, what do we have to be? So take a second, look back through your notes and fill those in. All right, now go ahead and check your answers, see how you did. All right, and then you're going to see these types of tables. So you're actually going to be doing some practice with these kinds of things in class where you're going to have different isotopes. I'm going to give you information and you must fill in the missing information. So for example, I'm going to do platinum for you and then we'll do a couple and you'll check your answers. All right, so for platinum, let's start with, I typically fill in all my numbers and I do my symbol last. But when I look at the name here, what is the name giving me? Remember, when you write the name, it's always the name dash the mass number. Make sure you're writing that correctly. So we want to include the mass number. So when I see this number on the end, 198, that tells me my mass number is 198. I also know that platinum is on my periodic table, and I can find atomic number from that. So I can look on my atomic periodic table for platinum, which is PT. Should know your element symbols by now, or be working towards it. So that's PT, and it has an atomic number of 78. So I look at the atomic number of 78, which then I know atomic number and number of protons are equal, so they should also be 78. And I also know protons and electrons have to be equal, so electrons also must be 78. Now, the only one that's tricky to find is the number of neutrons, but remember, we just take mass number, which is 198, minus my number of protons, which is 78, to leave neutrons behind. And so when you take 198 minus 78, we get 120 for the number of neutrons. So then we want to take this and write our symbol. Remember, when we write the symbol X, whatever our symbol element is, we're always going to put mass number on top and atomic number on bottom. You need to make sure you're writing it this way. I will count it wrong on a quiz or a test if it is not written that way. So platinum is PT, and my mass number is 198. Be careful that you don't accidentally use the neutron number, and my atomic number is 78. All right, so go ahead and take a moment, pause me, and fill in the rest of this, these other ones, and try them on your own and see how you do, and then we'll check our answers. All right, so go ahead and check your answers. Yours should look just like mine. If yours doesn't look like mine, then you're going to lose points. So for example, you should make sure that your name has the mass number following it, and you should make sure your symbol has, to the left, written mass number on top, atomic number on bottom, and then check your numbers. All right, let's look at, write the complete element symbol for nitrogen 15, and which of the following are isotopes. Again, pause me, try these on your own, and see how you do. All right, so to write the complete element symbol for nitrogen 15, I'm giving you a hint here when I say complete. I mean, don't forget your mass number and your atomic number on bottom, because the mass number was given to me following the name. So mass number was 15 over 7. Make sure that you didn't put 14, because if you put 14, that means you were trying to use the mass number on the periodic table. Remember, we always use the mass number that's provided to us. We never use the mass number on the periodic table because it's not truly a mass number. That is an atomic mass, and it's a little bit different. Which of the following isotopes are the same element? To be the same element, they have to be the same number of protons, so because they'll have the same atomic number. So to identify which ones are the same, we're looking at the ones that have the same atomic number, which is 10, so A, C, and E. If we looked at X, element X is actually 11 protons. That is sodium. Element X in D has 9 protons, so that makes that fluorine, and 10 is these are all neon. So if you were identifying what they were based on their number of protons, you can see that these ones all are the same element. Okay, so that concludes our notes on atomic structure and isotopes. We'll be talking more in depth on this over the next week or two, so please make sure that you write down any questions. You can see me or Mrs. Engel for tutorials, and she can help you with any questions that you might have, just like I could.